We learned so far. We start talking about a sequence. We say that to analyze a sequence, let an or f of n be a sequence. We're interested in the behavior of this sequence by analyzing the terms and eventually when n goes to infinity. If the limit of a sequence, let me write an, exists, it's equal to L or a number, we say that sequence is a convergent sequence. And if the limit of an while n goes to infinity does not exist, it means that either it's oscillating between two numbers or it's infinity, we say that it's a divergent sequence. For example, what we saw last time, if you have sequence a sub n equals to -1 to the n divided by n, by taking the limit of this sequence, limit of an, while n goes to infinity, this is the limit of -1 to the n divided by n goes to infinity, which is equal to 0. So your L, your unique number, is equal to 0, and we say that, hey, we have a convergent sequence. So our sequence is convergent. Another example for you. What if you have a sequence like this? A sub n is equal to -1 to the n. What's the behavior of this sequence? In step 1, we take a look at the terms of this sequence. N is equal to 1, A1 is -1 to the first power or -1. N is equal to 2, A sub 2 is equal to -1 to the second power or 1. N is equal to 3, A sub 3 is equal to -1 to the third. Okay, I got -1 back. N is equal to 4, I have A sub 4, which is -1 to the fourth or 1. Well, -1, 1, -1, 1. So it seems like this is the behavior of the terms of this sequence. Step 2, graph it. Let's take a look at the graph. One, 2, 3, 4, 5, 6, and -1 and 1. The terms of the sequence, the y values. When n is equal to 1, you get 1. When n is equal to 2, you have a +1, 3, -1, +1, -1, +1, and so on. Well, what's the limit? It seems like if n is even, the limit is 1. If n is odd, the limit is -1. So I don't get a unique number. It's oscillating between two values. So we can write the limit this way. Limit of an while n goes to infinity if n is even is equal to 1. If n is odd, it is equal to -1. 1 and -1 are not the same. The limit is not unique, so we have a divergent sequence. One nice theorem for us. I expect you to ask, what's the composition of a function and a sequence? This theorem answers this question. This theorem says, well, let the limit of a sub n while n goes to infinity be equal to f. It means that you have a convergent sequence. And suppose we have a continuous function. Then we can say that the limit of f of a sub n while n goes to infinity is equal to f of n. It means that the limit of f of a sub n while n goes to infinity, we can move the limit inside the parentheses to get the f of limit of a n while n goes to infinity, which is f of n. That's the meaning of that. So if I have a continuous function and I have a convergent sequence, I can move the limit inside and I can take the limit of the sequence and I have f of the limit. For example, find the limit of sine of pi over n while n goes to infinity. Okay, let's see. Can I use this nice theorem that I just learned? I have to check it. To apply this theorem, first check the limit of your sequence. Pi over n while n goes to infinity. Pi over infinity is equal to 0. So it seems like L is equal to 0. Now, what is the function? F of x is equal to sine of x, which is continuous. Okay, I have a convergent sequence. I have a continuous function. Now the theorem says the limit of f of a n while n is equal to infinity, which is the limit of sine of pi over n while n goes to infinity, is equal to the sine of limit of pi over n while n goes to infinity, which is equal to the sine of this limit is equal to 0 and sine of 0 is equal to 0. Nice answer. Let's take a look at this example. What if you have a complicated sequence? How do you analyze the sequence? Remember that in elementary calculus, you learn about sandwich theorem or squeeze theorem. The squeeze theorem says if f of x is sandwiched between two functions, like g of x and h of x, and suppose the limit of g of x is equal to the limit of h of x while x goes to a, and they are both equal to L. So the limit of the boundaries are equal to L. Squeeze theorem says then you can conclude that the limit of the middle function while x goes to a is also L. Let's take a look at this example. This example says find the limit of n factorial divided by n to the n while n goes to infinity. Okay. You can take a look at this intuitively and say that, hey, n to the n goes to infinity faster than n factorial. So you have something divided by infinity, it should be 0. By just using intuition and what we learned in elementary calculus. N to the n goes faster to infinity than n factorial, so you have a quantity divided by infinity, which is 0. Now let's take a look at the algebra. Some terms. What are the terms of this sequence? N is equal to 1. What do we have? We have n factorial. Remember that n factorial is defined this way. 1 times 2 times 3 times n. Okay. So if n is equal to 1, you get 1 factorial divided by 1 to the first power, which is 1 over 1. It is 1. If n is equal to 2, you get 2 factorial divided by 2 squared, you have 2 over 4 or half. If n is equal to 3, you get 3 factorial divided by 3 to the third, which is 6 over 27, or 2 over, let's see, 9. So as you can see, the terms of the sequence are getting smaller and smaller. These are the terms of the sequence. So it seems like it's getting closer and closer to 0. Very well. Now take a look at your general term. N factorial divided by n to the n. It's in between 0 and 1 over n. Using a squeeze theorem, the limit on the left is 0. The limit of 0 while n goes to infinity. This is a constant value. This is a constant function. It's equal to 0. The limit of right-hand side, your h of n, in this case, 1 over n while n goes to infinity, is also 0. So it means that the limit of n factorial divided by n to the n while n goes to infinity must be 0. Also note that here we have this situation. N factorial is 1 times 2 times 3 times 4 times n divided by n to the n is n times n times n, n times n times n times n. If you look at this term here, 2 times 3 times n divided by n times n times n, this quantity is always less than equals to 1. This is always less than equals to 1. You have something on the numerator which is less than the quantity on the denominator. So it's like, you know, having 3 over 31 or having 5 over 125 or something like that. Your numerator is less than the denominator. It means that it's less than equals to 1. So this quantity is less than equals to 1. If you multiply both sides by 1 over n times this times n, n times n times n is less than equals to 1 over n times 1, which is 1 over n. And it's always greater than 0. You are looking at the terms. So since the terms are all positive, it's always greater than 0. So that's why we can conclude that the limit is equal to 0. This is your numerator. This is your denominator. Numerator is less than the denominator. That's why it is less than equals to 1. At most 1. Very well. So let's take a look at this example. So suppose we have these two examples. We want to drive a conclusion. This example says, analyze this sequence. What's the limit of 1 over 2 raised raised to n while n goes to infinity? And what's the limit of 2 to the n while n goes to infinity? So the first limit is easy. A half raised to the n. This is 1, 2 to the n. And goes to infinity. This is equal to 0. It means that the sequence a half to the n is convergent. And what about the limit here? You have an exponential function here, which is discontinuous. It means that if you graph it, the graph is like this, 2 to the n. It goes to infinity. So the limit of 2 to the n while n goes to infinity is infinity. It means that this sequence is divergent. So conclusion is that, okay, let's take a look at one example here. So suppose you have this sequence, an is equal to 1, is it 1? No, it's 3. 3 over n plus 1. N plus 5. So method 1. Our first method is to analyze this using elementary calculus. Elementary calc says, we'll treat this as a function. F of x is equal to 3 over x plus 5. We'll take the derivative of this function. The derivative of the numerator is 0 times the denominator minus the derivative of the denominator times the numerator, which is 3. Negative 1 times 3 gives you 3. Divided by x plus 5 squared. Okay, your denominator is always positive. Your numerator is negative. It means that this rational expression is always negative. What's the meaning of that? It means that we have a decreasing sequence. Method 2, the definition that we just learned. So let's see, what do we have? Our goal is to create this fraction. N is less than equals to n plus 1. We know that. This is from the domain. So since n is natural number, it's always true. N is less than equals to n plus 1. I'm going to add 5 to both sides. N plus 5 is less than equals to n plus 6. Now, if you have a less than equals to b, 1 over b is less than equals to 1 over b. So 1 over n plus 6 is less than equals to 1 over n plus 5. Now I'm just having 3 to be added here. By multiplying 3 to both sides, you get 3 over n plus 6 less than equals to 3 over n plus 5. It means that an plus 1 is less than equals to an, which is meaning that you have a decreasing sequence. Perfect. Definitions for you. Okay. Definition of a bounded sequence. Bounded sequence. So we say that sequence an is bounded above if there is a number like m there is m as a number such that the terms of the sequence, the y values, a sub n, they are less than equals to m. M is just a fixed number. Eventually, we can treat this as a constant function, and these are the terms or y values. So we say that it's bounded above if y values of your sequence are less than equals to a fixed number. And we say that sequence a sub n is bounded below if you can find a fixed number or a constant function if there is m such that m is less than equals to an. All the y values, all the terms of your sequence are greater than or equal to a fixed number. And in general, we say that a sequence is bounded if it has upper bound and lower bound. So a sequence like an is bounded if an can be sandwiched between m and n. It has both bounds, lower bound, and it has the upper bound. Finally, our theorem says if an is increasing or decreasing, and it is bounded, then we can conclude that it is a convergent sequence. Either increasing or decreasing. If it's monotone and it's bounded between lower bound and upper bound, for sure you can say that, hey, I have a convergent sequence.